This is going to be interesting. So, I don't even know if I prefer to use GeoGebra or freehand it. I want to use GeoGebra. When I express opening new cache by accident. GeoGebra. I'm going to use the... Okay, so here's a circle. Okay, this music's a little too dramatic. We can go back to ambient music now. After an hour of the rock. Alright. What is RMM? Romania Masters of Math. Okay. So there's like a random point X. Okay. Okay, so it's A1, B2. So B2 is reflect. Line O, line A1X. Oops. No, redo. I want to move just this point. No! Haha. Okay, and then B3 is the reflection of... Thank you, Firestorm58 for the follow. A2 over perpendicular. Line A2X. And then B1 is the reflection of A3 across the perpendicular line from O to line A3X. Okay, so those are our diagonals. This is GeoGebra Classic 5. I did RMM. Sort of true. I did the RMM as a TST. I was not on the RMM team because I bombed the December TST. And, okay, so there's these circles. Yeah, this is gonna be hard to draw. So let me think from how do I draw these? Like how do I draw them? Okay, I think I know. T1 equals intersect the in-center line to the in-center of B1, A1, A3. Is that a command? Is in-center a command? We'll find out. If it's not, I'll have to change the triangle center one. B1, A1. Also, I don't know how this... I'll just call it L1. Okay, I'm just gonna call it L1. In-center is not a command. Okay. I got helpful there for a little bit. Triangle center... Okay, we're gonna color this some random color, but if I'm correct, I think the point is here and here. So we're gonna call it T1 and we're gonna rename B to S1 or something. And then, oh geez, how do I get the tangency point? Okay, anyways, so I1 is the intersection of I have to do this 3 times, so people have a lot of time to read this problem. A1, B2, perpendicular line. I hope this is right. I'm just trying to draw a diagram with GeoGebra, and it's a struggle as this condition is so bad. Okay, that's 1. We did it. Okay, so next, L2 is line. So for people that don't know what this is, there's a lemma that actually let me draw it and I'll see what it is. A2, B2, B3, 1. I almost want to keep these lines in the picture just out of curiosity if they'll do anything. No, you go here. You are green. And you points I still want to be blue. No. Okay. Frick. Oh man, I messed something up. What's the... That's it. It's not even a mixed linear though. This is called a curvilinear in circle. It's rare and more confusing. But the lemma that I'm using is that this green line, it passes through, it turns out the end center of A1, A2, B2, and the end center of A2, B2, B3. So what you do is you extend this, draw the end center of this triangle, draw the end center of that triangle, and that gives you the green line. That's how I'm constructing these. And then the end center here is I take the perpendicular here. So I2 is intersect perpendicular line of T2 to line A2, B3. Yeah, so it turns out knowing your geometry well makes GeoGebra easier to use because you know stuff like this. Oh jeez. Okay, they were supposed to be black. I somehow colored them blue. I want them to be black. Black for consistency. Black. Okay. Circle I2, T2. Almost there. One more. Okay. L3 is line through triangle center. B1, B3, A3, 1. Triangle center. B2, B3, A3, 1. Okay, that's the last green line. Okay. So here's T3. Here's S3. Okay, and then I3 is why didn't that render? Oh. Huh, that's not right. Okay, this green line's messed up. What did I do? No. Okay, B1, B3, A3, B2, A2, it's A2. Okay, circle, I3, T3. Alright, retrieve the diagram! Oh, Jesus. That was long. Oh, there's so much stuff happening in this picture. Okay, and like the case we're interested in is like I want to see if I can get all the points on his circle, right? If I get one on, do the others go on? No. Oh god, I have no idea what's going on. There's so many degrees of freedom. What the heck? Shoot, how do I get all 6 points on one circle? What the heck? Ah! I don't know if I can. It might not be the case that there's a choice for every A1, A2, A3. What if I do a really degenerate case where these are like diameters? Can I get the 6 points to be on a circle? Are you kidding? Okay, never mind. We're just gonna try to do the problem first. And the reason is that like when inequalities are tight like this, they often over-constrain. Like it's not just 1 degree of freedom, it's often like way more than 1. Okay, so I have to actually do the inequality now. R1 plus R2 plus R3 is at most R. Huh? What am I supposed to do? What is this? Okay, we're gonna hide this circle because I think it won't really be relevant. I mean, I feel like the cyclic might just come from... The cyclic's pretty well behaved, right? Because it's a statement about the power of a point. It's like this times this is Wait, if there's cyclic, doesn't that mean like all these lengths are equal or something? Like these 6 lengths have to all be equal? So it's like a regular hexagon? Right? Wait, yeah. So if they're actually cyclic, then like x, like the power from x to here is times this is equal to this times this. But because these are equal, that can only occur if like x s1 equals x t2 and similarly. So okay, this blue circle is not helpful. That's just bait, and it's saying that if equality holds, then these 6 guys are the vertices of a regular hexagon. That's it? Okay. No, not regular hexagon. Sorry. Not. What do you call it? Whatever. It means that this lengths are all equal. So okay, this circle is not that interesting then. There's something much stronger happening. If they're actually, in the case where they're actually equality holds, then there's a pretty strong statement that the distance from x to each of the 6 circles should be equal. Okay, that's fine. So let's focus on proving the inequality then. How am I going to get a control over these radii? Well, there's like some homotopy scale factor happening, right? I don't know what to do with that. What do I do with this point x? Sorry, it's not regular, but if they're cyclic, then x, like, x s1 equals x t2 by power of a point, because these are equal, so this times, yeah. By power of a point, you will get that these 6 little segments coming out of x all have equal length. Draw arc midpoints, what will that do? Actually, oh, that makes a lot of sense, actually. Yeah. Okay. Alright, so I need to, oh man, I was hoping I wouldn't have to construct these points because they're really hard to determine. Okay, whatever. Okay, so TSP, we call it P. P1 equals intersect line OI1 and line. Wait, what else is it on? Ah, dang it! I don't. I'm just gonna use the raise. I hate doing this because it's like, I don't know. But I don't think I have a way out. It's like not uniquely determined or something. Like there's two intersections, so if you try to do things, it might confuse GeoGebra later. But in this case, I don't. It needs to distinguish the in circle from the X circle, the mixed linear, sorry, curvilinear in circle from X circle. So I think I have to actually do it. And just bite the I3. You know, I don't like the point names anymore. I think I'm gonna use UV. Because we should reserve T for the tangency point that's like to both circles. I think that's a more. This is a slightly more intuitive naming. Obviously, it doesn't matter, but do the 6 points lie on a conic? I can check. They probably do, honestly, but I don't know why that would help. Oh, they don't. Okay, never mind. I was wrong. Yeah. If they're concyclic, with center X, which can you use 6 points lie on a conic? Yeah, I checked conic. Yeah, I checked conic and it's not there. No, I checked if they were on a conic and they weren't. I think it's a reasonable guess, but conconic? Why don't you just say coconic like a normal person? Okay, so yeah, what's the point of these arc midpoints? Well, that means alright. Let's shoot everything out. I don't know if this will do anything. I mean, they'll meet at the arc midpoints by homophily. I just don't know if that helps at all. I'm actually curious what happens if you use Pascal's theorem on this. I don't think I'll do anything, but we can try. Oh man. Also, sorry, I'm gonna do this with the name lines named properly so I can find them later. T3. Okay, so, well, let's define the arc midpoints first. So this guy up here is like M1, I guess. M1 equals intersect line T3 V3 line T2 U2. M2 is intersect line T1 V1 to line T3 U3. And M3 is intersect line T1 U1 to line T2 V2. So these are our three arc midpoints, and there's a bunch of lines. M1 T3 is pretty diagrams. M3 T2. Okay, great. And the advantage of naming them consistently is I can actually select them here and change them all at the same time. If we're going to do something, do it well. Crap. No. Okay, so what does this do? Well, I had to leave an hour ago. What did I miss? Not much. I started the geo problem. Honestly, that's basically it. Okay, so what happens if I do apply Pascal? T2, M3, T2. Oh. Probably nothing, but I'll try it anyways, just out of curiosity. I don't think this will do anything. So Pascal on T3, T1, sorry, M3, T1, M2, T3, M1, T2. So M3, T1 intersect M3, T1 intersects T3, M1. Oh hey, actually it might lead to a statement. I don't think it leads to anything good. Okay, never mind. That's too many random points. Yeah, I don't see how I'm going to like I almost don't know what the big circle is doing. Like I feel like I have this the circle omega is like I don't know. Would Casey's theorem be useful here? Maybe. So I think my reservation about Casey's theorem is that I don't know Casey's theorem. That's the actual problem. I don't know the theorem well enough to apply it. I agree this looks like if you're gonna use Casey somewhere, it's here. I just don't know the theorem well enough. And I have a slight aversion to using theorems on stream that I'm not familiar with because it usually ends in disaster. But yeah, if you're gonna use Casey, it's here. What would you do with it though? Let's see. Because I need some way to control the radius, right? I need to get an R1, R2, R3 somehow. I could get it based on the angles. Like there's 3 angles, and like if I relate the tangents and then it could work. It's a bit of a stretch, but what would Casey's theorem say? Casey's theorem applied to what is Jacobi theorem? I actually don't know. I hear that name every so often. I haven't figured out what it means yet. Like, how do I get control over the radius? I think the one thing that looks like the radius is something related to like I don't know. I have no idea. How do I control the radius? It has to. There has to be some sort of homotopy here, right? Because why? Well, it's just not going to work otherwise. I need the radius. Like for example, R3 is like T3 V3 against T3 M1. Can I use that somehow? It's like V3 U3 divided by M1 M2. Can I get control over this length? Evan, what is your favorite hyperbola? Beats me. Maybe the... far back. I'll say far back. Oh, that triangle's very... I think I have too many yellow segments. I should just focus on some of them. I'm gonna focus on the ones from 3. So we have this thing, and then we have this MMM. No, sorry, I want the ones that use T3. It's like T3 V3. Yeah, it's U3 V3 against M1 M2. Where can I control that ratio at all? What is the Feuerbach hyperbola? It's the hyperbola through A, B, C, I, H, in center, orthocenter. What did I do? Wait, M3, M2, I kind of know explicitly based on like the angles in the problem, right? And do I know anything about U3, V3? It's like the lengths from X, and oh no, it's not. U3, V3, T3, no, they're not similar. It's just the homotopy. T3, V3, U3, and T3, M1, M2 are similar. Like V3 is parallel to M1, M2, but T3, V3, I don't know if there's anything I can really say about it. Well, maybe, So, like, I can, maybe, no. Oh, shooting llama. M2 times U3, M2 times T3, T3. Yeah, I don't know. I don't know if T3, the T points are helping much. I just feel like I don't have any good control over V3 and U3. It's just like, yeah, what do I do with these points? Can I say something about like X V3 against X? Are U1, U2, U3, and V1, V2, V3 similar? We can check. I'd be surprised though. Or yeah, no, they should actually no, they should be, right? Or wait, X is Let me just check. So the thing is like xu1 equals xv1 and so on. So I think there's the triangles are related somehow in the sense that okay, how do I check it? u1, u2, u3, v1, v2, v3. Alright, so they're not similar per se. It is true that xu1 equals xv1 and that's like the strongest thing I have right now, honestly. If I draw just the x's and the 3 red circles, is there a unique giant black circle tangent to all 3? It should be, right? u1, u2, u3. I agree Desargues applies because their something corresponds. I don't know if that helps. What I want to say is I want to imagine I start with the red circles. Like, I start with the 3 lines. I draw 3 red circles arbitrarily. There should be a unique black circle tangent to all 3. Like, I feel like I should start with the red circles and draw big omega last, and big omega will cut out the points A1, B1, or whatever that we're never even really using. I just don't understand how I'm supposed to calculate the radius. Like, given R1, R2, R3, and all the relevant lengths, can I calculate the radius of the large circle tangent to all 3? Descartes? I don't think that applies here. Descartes is like if you have like 4 circles and every pair of circles is tangent, yeah. Yeah, I want to start with the 3. I want to imagine I start with the 3 black lines, and then draw the three red circles however I want inside each of those things, and then there's a unique giant circle that's tangent externally. Sorry, internally. This is internal tangents. Internally tangent to all 3 of the red circles. And I don't see how you do that, but it feels like that. Because it feels like the big circle doesn't really do anything other than give the value of R or something like that. The red circles are special though? How are they special? How many distinct circles can be tangent to a set of 3 circles? I'm pretty sure the answer is 2. Which is why I'm saying this. Like there's a 1 internal and 1 external. Like I think what you should, I feel like if I didn't have this black circle here or any of these 6 points, and so I guess I have to hide the M's as well. If I just start with this picture, and hide all of these, oh my god, there's a lot of points to hide. If I start with this picture, I think it's almost certainly the case that there are, yeah, I think there's 2 circles outside. No, I feel like the way I imagine is you start with a circle that envelops everything and you shrink it until it's tangent, and I feel like that should be done in exactly one way. yeah, like I really want the red circles first because I want to control those parameters. But I don't understand how I'm supposed to get the radius of the main circle after that. So this circle I think is definitely unique, and I don't see how I'm gonna do anything with it. Can't you do one circle? Thank you, Alan MD, for the follow. What's the Apollonius Theorem? What's happening? Okay, I agree there's 8 circles that are tangent in some way, but if I require all the tangencies to be like on the outside, then there should be 1, right? Like there's one here, there's like another one here, and I can get another one where it's like that or whatever, but like I think if you like the problem, I'm looking for the one that's like the largest one, the one that's like tangent to everything. Yeah. So it should be 1, right? If I require all the tangencies to be yeah. You want me to use Casey's theorem? I might have to, actually. I was hoping not to. Okay, yeah, maybe we have to use Casey. Alright, how does Casey's theorem go? Casey's theorem. Munch? What does Munch do? I see the external tangents, I guess, but like... Yeah, Casey's is like Ptolemy's, where in this... Can I have the arc midpoints back? Sure. Oh, actually that's smart. If I use Casey's theorem, with like the 3 circles and one of the arc midpoints, does that do anything? It's like the power of M1 or something. I don't like it, honestly. I feel like I should be using Casey on like red, point. How to use it with 3 circles? You don't. It's like we just have to add a 4th. We have to add a 4th quote-unquote circle, which will probably... If we're trying to use Casey, we should add a 4th point and call it a circle radius 0. Casey with 3 red. No, X doesn't lie on the giant circle, so it doesn't work. Another 4. Fix omega 1, omega 2, vary omega 3, and then 4 points of a cyclic with what? U3, V3 at the same time? We would use Casey cyclically, I guess. I mean, Casey is fine, I just don't see where it's gonna go, or something like that. Alright, good night. Yeah, like, I can write down all these length relations, but I don't I don't see why that tells you anything about what we're actually trying to compute, right? The thing we're actually trying to compute is the radii, and it's like not related. Like nothing we're proposing like actually uses this. Do the cyclic quads from the shooting lemma do anything? You tell me. So like for example, if I tilt my head and then like, I don't know, like T1, like M3 has some cyclic quads. Like from each of the arc midpoints, yeah, you get these cyclic quads. So T1, yeah, these 4 guys are cyclic. But again, like, how do I get the radii? That's something I really care about. The best thing I have is that the ratio of R2 to capital R is like whatever T2V2 against T2M3 is. So yeah, that's something. But what does that do? I don't know. I don't know, there's homotopy. I know there's homotopy. I just don't see what to do with it. I almost want to take the homotopy from the red circles to each other, but I don't know about anything either. Like T2, T3 intersect A2, B3 will be the center of some homotopy between the red circles or something like that. But I don't know what that does. Yeah, I don't know what X does either. Like, if you're, let's say we're looking for T1 from T1, right? Like, this segment is like I want U and V1 over M to M3 to. You want to use Barry? Oh lord, how does that help? Yeah, there's homotopy at T1. That's basically all I know. I don't see how to do anything else. Fix omega 1, omega 2, X, and vary omega 3. I don't see what that does. Like, the circle will just change a bunch, right? What's M1 again? It's the arc midpoint of the arc A2, B3 not containing either of the red circles. M1, M2, M3 is similar to a triangle defined by U1, V1. By those three, the green one? I mean, I guess. Yeah, they're similar because they... opposite sides are parallel. That is true. So this green one and this light blue one are similar. So they're homothetic? I don't know if that does anything for me though. Can I draw T1X? Sure. That's T1X. No, it's not concurrent with the green ones. Yeah. I also considered seeing if like N3X line through M and X, line through like, I don't know, more random stuff. But yeah, this diagram is really weird. I don't know what to do with it. Freaking. What am I supposed to do with this? Jeez. How's your CMO grading going? Very slowly. Yeah. Everyone's tired. I scheduled you CMO grading tomorrow morning at like 9 AM to make sure I don't just sleep my Saturday morning away. So I have another 3-hour shift tomorrow. Draw the internal tangent circle. When, yeah, they are cyclic exactly when X is the center of the circle. That's what we've just found out. And that's my power of a point from X. Like, if they're cyclic, then... I think drawing tangents MI just finishes like Prime's entrance 2018 thing. What? Huh? Whoa, what? You want me to draw the tangents at each of the MIs? Okay, well now I'm gonna have to zoom out. Oh crap. Okay, so I draw these two tangents. Okay. This is supposed to finish? Why? What? I want to hide triple M. So these are tangent, or like, so the... Oh, what the heck? Is that what's gonna happen? I don't believe you. Are you serious? You're joking me, right? What the heck? Wait, how does equality hold then? What? No, 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 no. Wait, how does equality possibly hold? Well, actually, I can just draw an example where equality holds. It holds when t1 equals m1? You need ti equals mi. Oh my god. No way. No, 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 no. Are you kidding me? What? Okay. So for people who don't know what we're talking about, a long time ago, in a universe far, far away, Prime's entrance exam 2018 happened. And okay, where is it? Prime's USA entrance exam. How to apply, and then here's 2018 problems and solutions. I'll just go to solutions, and I'll tell you a little bit of story about this problem, because I wrote it, and the reason I wrote it is because I had some other problem that was rejected from the problem set, and so wait, no, it's not 2018, 2017 or 2019. 2019, yes, yeah. I was like writing the solution, and I write this for the primes folks, and they accept some of the problems, but sometimes they're like, I don't like this problem, can you replace it? And so this was a problem I made up like at the very last minute, because I was like, we were at the deadline, and one of the problems I got rejected, and I needed to fill in something, and I'm like, and then I just drew this picture that looked like this, and I was like, okay, let's make a problem out of it, and then I did, and I thought the organizers wouldn't like the problem because it was something I made up at the last minute, but they said this problem was great, and I'm like, okay, all right. I made it up at the very last minute as a throwaway, but if you like it, I guess that's good. I think it's nice. I just think it's really easy. And what happens is basically if you compute the homotopy ratios, like the sum of the homotopy ratios from this guy plus this guy plus this guy is the homotopy ratio of the whole triangle. This is immediate out of vary. Yeah. The result is very nice. It's just not. I think it's just easy though because it's you kind of know exactly what to do. Yeah, I do think it's actually a pretty good problem. It's just easy is the thing. Like it's not good for using on an exam because everyone just solves it and it doesn't say anything. But as a result, it's very nice. So TLDR ratio plus the sum of the ratios is exactly equal to the ratio of ABC. Now, why is this relevant? Well, here we have this blue triangle at some random point, and then these black lines. And so the ratio of, if I complete the picture, the ratio of the in circle of like this triangle, and this triangle is like the, forget this yellow stuff. Forget the green stuff too, we don't need any. What the heck? So if I imagined completing this picture, jeez, I need. So if you imagine completing this picture with these three lines, then by the thing that I just said, the ratio of the yeah, the ratio of like this in circle plus this in circle. Basically, the sum of the in circles if the red circle is the in circle of the triangle rather than just inside it. Oh, frick. My bad. Here. So here's the picture with a bunch of stuff deleted. And the point is that if I imagine expanding the red circles so that they fill the in circle, yeah, imagine. Yes, I imagined it. Yeah. Expand the red circle so that they are the in circle. Then the sum of the radii would be exactly capital R. Like, period. And the red circles are smaller than that. So that proves inequality. Inequality holds if and only if like t1 equals m1 and then t3 equals m3 and t2 equals m2. So i.e. like yeah. That's extremely constrained because it tells you that x is equidistant from. I think that's good enough to imply that x is equidistant from a1, b1, a2, b2, a3, b3, i.e. that x is the center, like x coincides with O. And let's see if I'm right about that. I think it's that plus something else. No, wait. When are they equal? When does t1 equal m1? It's like... no, sorry, that's not quite it. So I know that, okay, OI1 T1 is always... When are they equal? So they're equal if... When does T1 equals M1? See, I can't even get it with a regular hexagon. Crap. How are they not equal to a regular hexagon? Are you kidding me? Dang it. So when is Ti equals to Mi? So that tells me the OM1 is perpendicular and OIT1 are collinear. So that means that okay. Yeah, so I think R1 equals R2 equals R3 in that situation though, because you need this line to be... If you imagine this line is horizontal, then A2, B3 is horizontal, and I1 is supposed to... Like, this is supposed to be perpendicular, so... I don't know, what does that imply? It's very constrained. God. Yeah, so it's like O1, I1, M1, so we're talking about part B. So it's only if the arc midpoints. What I don't understand is how it's not equality at a regular hexagon. Did I mess something up? I messed something up. Am I just bad at drawing regular hexagons? 1, 2, 3. Oh, this is 3/5. Okay, let me just widen. Let me zoom in a little so that I have more grid lines. 1, 2, 3, 4, 5. Okay, I want A1 here. I'm really bad at guessing what 60-degree angle looks like. Yeah, it should be a picture that looks something like this or something similar. Yeah, so this is the equality case when they're actually expanded to hit them. I think it's probably not the only equality case though, although I might be wrong about that. Let's see. No, oh, X has to actually be the incenter in that case, right? Let's see, so O1, I1, M1 are collinear, and then I'm asserting Ti is there, so T1, I1, O1. What's true about X in general? X1, I1... It's gotta be, right? Yeah. X lies on the perpendicular bisector of v1, v1, and that's we're basically being told the O is equidistant. Yeah. So I think it has to be either this picture or a slightly non-equilateral picture. I'm just gonna draw this on paper quickly to get a sense of what I'm doing. No, it doesn't work. Yeah, this is actually. I think it actually has to just be. Oh, that's true. Well, yeah, if X is the center, we're okay. Well, X is the center of the incircle capital omega. It's unclear if that's good enough for something. Can I do a problem request now? Probably not, because there's another like 6 in the queue already. I think I'm just being dumb. I should be able to work this out. So, what are the statements that are always true? X1. So X1 is. Let me just actually do it. This shouldn't be hard. Famous last words. S1 is on the perpendicular bisector of U1, V1. Always. O, I1, M1 collinear. Sorry, T1 collinear. And then M1 equals T1 is what we're being told. So OI, M1 are collinear, so what does that imply? Okay, wait, let me go back to a generic situation for a moment. Like in general, if T1 equals M1, so the angle bisector is at right angles. Right. So that means A1, B2, and 8. So that would mean that, yeah, angle. So this means that the lines XA1, XB1, and M1 form an isosceles triangle. If I know the angle bisector does that, yeah. No, what? Work it out, work it out. Yeah, so, and yeah, XA1 is parallel to, so, yeah, lines M1, M2, M2, so M2, M2, and M3, M3 are reflections across the direction of M1, M1 or whatever. Wait, I'm like really confused. It's just because I keep getting X and O confused, and because I'm pretty sure they're the same point. Here, let me. So it's OIT1 collinear. Like, how do I use T1? It's like, or sorry, how do I use M? No, T1 is the tangency point. What am I talking about? Oh, okay, yeah. No, yeah, I am trolling. Yeah, T1 M1 doesn't tell you anything. It just tells you. What does it tell you? Work it out. Don't be dumb. Work it out. So yeah, T1 equals M1 doesn't seem to actually give you very much information directly. It tells you that you have that. So what does that imply? Yeah. So what's going on? I know T1 equals M1 and I can't figure out what that implies. What does K12 say? U1 V3 and U2 V1 intersect at T. Oh, yeah, okay. Yeah, that's a true statement. Shooting lemma, yeah. If the midpoints coincide with the tangency points, then a bunch of stuff happens, and now I have mass shooting lemma. So what does that do? How does that give you power of? Oh no! Wait. It's actually that they're cyclic. This is a scam. So you're saying that by power of a point, it gives you like U3, V2, V2, U3, V3, U1 cyclic. Are you serious? Okay, so from our duplicated point. That's absurd. So T3 V3 time is equal to T3 V3 times T3 T1 is equal to T3 U3 times T3 T2. Also by shooting lemma, T1 V3 times. Actually, they're just equal, right? Well, they can't give pairwise distinct circles because if so, their radical axes would be like the TIs, and they're not. Use shooting once and apply homophily. Wait, what? What did I miss? Oh. Okay, fine. Yeah, alright, fine. So it's actually that the cyclic is actually what you're supposed to do. I thought it was I thought it was for sure bait because it's equivalent to x being the center, but it's not bait. What just happened? I can't believe this. What the heck? What? No, why? How is this problem made? I have no idea. Okay, here's my actual question. Why is this problem 5? What was problem 6? No match is found. I apparently haven't done it yet. I don't. Okay, well, now I gotta know. What are the scores on this problem? Well, the RMM server's down. Okay, great. Do I use this one? Archive.org. Is it not just me? Like, I feel like I just can't get the I couldn't get the RMM website to load. Is it just me? RMM is in. So RMM used to be really hard, and I think it's been toned down in recent. It used to be advertised as a contest that was harder than IMO. Like they said, 1-4 would like not be, you know. Sometimes RMM 1-4 would just like not be IMO 1-4. They'd just be like medium hard type problems. Yeah, I don't think that's been as true recent. I think in recent years RMM 1-4 is actually a 1-4 level problem instead of some like abomination that's way too hard for its place. Yeah, I can't access it, but that's why we have archive.org, where we can see. Okay, well, that's RMM 2016 for you. Nice job, Bishon. 1, 2, 3. Hey, that's not as bad as I thought it would be. Wow, we did really well on that problem. Good job, USA. Yeah, that's RMM. What would I rate RMM 2020 problem 2? What's RMM problem? I'm not sure. I didn't solve it. But I didn't try very hard. But I also didn't solve it. Yeah, problem 6. Well, congrats to whoever. James Bond. This just happens like somehow. That's what happens when 5 and 6 are both hard. You know, it's like IMO 2017. You know, problem 2 and problem 3 are both tough. Everyone's going to get problem 2, and then problem 3 goes down in history. This is what we in the business call James Bond. Poor guy. That's the only solve on problem 6. No one else got it. That's the only. It's not just that it's 007. Like, that happens all the time. Like, 007 happens all the time. But I think it's just hilarious that. Wait, is this a second solve? I saw 15. There's a 3. Yeah, I just thought it's hilarious. The only solve is a James Bond. That happens every so often. Not every solve. That's pretty rare. Okay, what is this RMN problem 6 though? I want to see now. I love archive.org. Haven't done it before. Someone else do it. Oh, I remember this problem. I don't remember problem 2 at all. Okay, anyways. We did it. We made it. Man, that feeling when, like... I wrote the primes problem. And I did not see it in this problem. Oh, okay. Smile. Okay, I have to do Jadon's problem next, right? Or no, I have to do 1985 NA first.